Our first presenter is Joshua Hyde, so if you could join us, Joshua. So Joshua's doing a Bachelor of Engineering, focusing on electrical and electronic engineering, and I'll just bring up his presentation here.
And my project's not electrical engineering based, it's more...
No, that's exactly right. So the diversity of these projects is that often the student comes from an area that is totally different from the discipline that their project...
And then sort of broadening your horizon, basically.
Exactly right. So this particular project is looking at measuring and modelling the hand movement of children with cerebral palsy. So,
all right. Good morning, everyone. And this is my presentation. If you don't might know me already, which most of you do, I'm Josh. So my project is a 3D hand modelling for children with cerebral palsy and tracking hand movement. So let's get to the next slide. So just a bit of background about cerebral palsy. It's a range of conditions that affect the way the brain processes messages to the muscle movements. It's not specific. There's 4 different types of cerebral palsy and 4 different ways it presents itself. It's caused by injury or damage to the brain in pregnancy or childbirth. It's the nature of the injury that's caused is not known. Presents in many ways depending on the individual, so each individual's different. Some will gain strength in childhood with or without corrective surgery, but early intervention's really important. And this is where this project comes into play. So my project basically is to compare the accuracy and angle capture and visualisation between the IMU, which I'm using the Xsens App, and the optical sensor, which is the LeapMotion. An optical sensor for the LeapMotion is not one where you attach a suit on and have the nodes. It's actually a sensor where you can use your bare hands, so that makes life easier. And so just comparing the accuracy and the angle capture and the visualisation. All right, my timeline. So some of these come in together, basically. So literature review, so basically reading a past thesis paper of one of the students that's done this project before. Teaching myself some Unity in C#, and I can tell you C# is easier than C++. And then from there, testing the capturing the angle and the formula or the mathematical script that I wrote to get the joint angle for the LeapMotion, and then testing the UDP streaming of the Xsens App on the computer or in Unity, which unfortunately doesn't work in here because the routers don't like it. Works at home, so I can't really demonstrate the Xsens App, but I can demonstrate the LeapMotion to you today. And then from there, finalise the Xsens dot tracking, same with the LeapMotion, so finalising Unity build, making sure it looks good, validating both methods at home, so it's not a proper data validation, and we're actually going to validate it properly next week in a validation lab. Fingers crossed, hopefully no hotel quarantine leaks between now and then. And then from there, prepare the report. All right, so the Xsens App, and I might have to come down here. So it's a self-contained IMU. So IMU stands for Inertial Measurement Unit. It also stands for many other things. It's got 9 axes of freedom. So, and the IMU, basically, it's got a gyroscope, a magnetometer, which is something I didn't need to use, and the accelerometer, so it measures those 3 things. It's got the Xsens has a native app for both Android and iPhones, which you can use to get Xsens data. Unfortunately, in this case, because I do need live streaming, I can't use the app, so this is where the iPad app Kind XYZ gets into play, and I'll come to that shortly. LeapMotion, optical tracking device that doesn't require a suit. has a built-in ability to track hands, and I'll show you that when we do the demo. Has a Unity software development kit, so that makes life easier, so you don't have to script the LeapMotion side of things. And it's got prefabs available, including your hands, so you don't need to model the hands either. Can track fingers and some gestures, but it can't track all gestures. Right, so getting the joint angle, just a bit of note, I don't completely understand Quaternion because it's complicated. And getting the rotation vector, the maths behind it's easy. Unfortunately, it's very tedious and not nice to look at. And I'll be forever here going through it if I do show you the maths. So anyway, the Quaternion of the hand and the arms are already given. So what we need to do to get the joint angle is find the common or a vector on an axis, so it can be X, Y, or Z. From there, with that, and make sure the X vector is the same for both of them, then you get your rotate vector with your Quaternion and your axis you're referring to. And then from there, you get your two rotate vectors, you get your dot product, which is pretty simple maths, and then get your angle using arc cosine. So simple maths again, because output in radians, you just convert it to degrees. Right, C# and Unity, I'll probably come back here. So other presentations probably don't cover Unity, but basically if you don't know what Unity is, it's a game engine. Do many things with it, but you can't do the modelling or prefab work, so you have to use something else like Blender or something like that to use it. Backscripting is written in C#, which is easier to learn than C++ because there's less syntax to worry about. Some of you are a fan of Python. Bad news is it's not Python. Me personally, I'm not a fan of Python, so I'd much rather C#. Alright, tracking with the Xsens dot. So the iPad app KineXYZ, when you first open it up, looks like this. So you have to plug the sensors in to turn them on. If you don't plug the sensors in, they won't turn on. Make sure your Bluetooth's on, and then you have your sensors will appear there, and then from there, drag the sensors across, attach them to the one to the arm, one to the hand, and then you'll see, you can't see it here, but there will be a little circle there. You click on the circle and it'll give you the values. Going from there, click that arrow, you'll go to this page, and then these are the values. Attach those values, that block code there, live streams, Quaternion values from this app into a UDP packet to the computer, and the UDP packet as a string, not as ones and zeros, looks like this. So basically you got your rotation of your hand and your arm, and then once that's streamed through, from there into the app moves a hand, and then the back scripting that I write to get the angle basically outputs the joint angle with reference to the X. So when you have your X angle, it's basically X0 there, but because your joint angle is a difference, it doesn't really matter. And then it's got a functionality where you can record your angles and raw data into a CSV file, and that's what it produces. So you see on the left hand side, that's your timestamp, and then these are your angles with reference to the X, Y and Z axis, and then these are all your position data for your hand and also for your arm. Your position is from Unity itself, and your Quaternion is from the app. Your LeapMotion, bit more straightforward. All you need to do is plug your LeapMotion in, find some blue tack, attach the blue tack to the LeapMotion, as long as you have somewhere to do it, and then open up the Unity build, stick your hand underneath it, and it'll show a hand. The values recorded is the same as the previous slide, and the way the angle's recorded and the CSV file is the same. The only difference is no UDP streaming, so you don't have to worry about this problem with routers or anything like that. And also, and I'll get to this later, the accuracy of hand tracking is more accurate with the LeapMotion. However, the accuracy in capturing your joint angle is not as good. So anyway, I'll show you, this is the first one's going to be playing. So you can see where I've put my hand underneath. The hand moves where the sensor detects the hand. You see the hand, twiggle my fingers, and I'll twiggle there. And sorry if this video is a crap quality video. It's shot on an iPhone 11 with a case on. Alright, I'll show you the next one. So that's with the Xsens dot. So you rotate your hand, and what should probably part of future improvements is making sure when you tilt your arm it doesn't tilt it wrong, but basically what you can see there is it directly correlates to what's shown in the app because it's merely just streaming UDP packets. Alright, outcome with some bit of quick at-home validation. Validating the two technologies, it's a win-win situation. So your joint angle, your Xsens dot is really accurate, and it basically very close to what the goniometer says by about 5%. If you do attach it to the hand, the accuracy will be affected because the shape of the hand and where the Xsens dot is. But your visualization aspect of it, the LeapMotion is a lot more accurate in that sense. And if you use both of these, that's great because you'll get more benefit. So anyway, thank you Savash for helping me out with this project, and same goes to you Ian if you're watching this on YouTube. And thanks to Wesley for helping out with the Unity and the technical aspects of it. And anyone got any questions or anything like that?
Please.